All right, there we go. So what I want us to do is look at each integral, and before we do any of them, let's just think about how we would do them. So we'll start with the first one, and I want you guys to tell me in the chat, what do you think? Like, what thoughts do you have about this integral? Yes, all right. So some people are saying sub, some people are saying trig sub, but this is arcsecant, right? This is exactly arcsecant. So when we look at this particular question, if you have to go through and do a U sub or a trig sub, is going to take you a lot longer than what you would necessarily need, because this is just a known form. So in terms of a final exam, the amount of time allotted for this integral probably wouldn't be that much because it's a known form. So here we can say this is just equal to 3. With arcsecant, do I need to do 1 over a? Yeah, I do, but a in this case is just 1, so that doesn't really change anything. But if that had been like x squared minus 4, it would be something to think about. So I'm thinking of like 1 over 1 arcsecant of x that I'm evaluating between root 2 and 2. Good. Okay, so then we're plugging in and we're gonna get 3 arcsecant of 2 minus 3 arcsecant of the square root of 2. So then how do we go about evaluating arcsecant of 2 and arcsecant of root 2? So this is something probably from last semester that we have looked at a little bit this semester as well. Remember what we're doing. We're asking ourselves a question. We're asking ourselves a question. When does secant exactly, Parnian, when does secant equal to 2? So like this would be, when does secant x equal to 2? But sometimes secant's a little bit hard to think about. So what trig identity do I have that allows me to rewrite secant? You got it, Tashi. So this is the same thing as 1 over cosine. So I could think of this as saying, when does cosine x equal to 1/2? So I could use my trig triangle if I need to. So like, depending on how you guys have memorized this stuff, like, do you have the trig triangle? Do you have like a little table to do it? Do you think of the unit circle? When does cosine of x equal to 1/2? Yes, Julie, you got it. And someone else had said it earlier as well. That happens at pi over 3. So x is equal to pi over 3. And then we're going to ask, when does secant x equal to root 2? So again, this is like saying cosine x is equal to 1 over root 2 or root 2 over 2. And that happens, good job, Abby, at pi over 4. So x is equal to pi over 4. So then my final answer here is just 3 times pi over 3 minus 3 times pi over 4, which is pi minus 3 pi over 4, which is actually just pi over 4 for my final answer here.
For questions like these, like if instead like you had to do like integration by parts, I always get confused about like where I would leave like the integration sign with the two points, and like where I should put it, like if you're doing integration by parts.
You mean like with the bounds?
Yeah.
Okay, when we get to an integration by parts problem, I'll add some random bounds. We won't plug them in, but I'll show you how we would do the notation when we do the integration by parts. Does that seem reasonable?
Yeah, thank you.
Cool. Okay, so are there any questions about what we just did here? And is it bad that I can change how we do this if this is too messy and hard for you guys to follow trying to do it on the sheet like this. Because like when I move, that's gonna happen. Do you guys want me to like do this on another sheet, or is this okay? Because I could like move back and forth. Okay, it's going to be a little bit more challenging, but so the next question we have is x e to the x minus e to the x. Maybe we'll just do it that way. I'm going to stop sharing this and share this instead. Okay, so our next question that we have here is the integral of, so hang on, we're doing the May 2013 final. So we have x e to the x over the square root of x e to the x minus e to the x dx. You got it, Tia, exactly. So like when you look at this one, maybe there's nothing like obvious that jumps out at you. You're not like, oh, clearly the derivative of the thing is there. But we do have a square root and we do have like a thing under the square root. So we have a clear thing to a power. So yes, so I could start off by letting u equal e to the x. I see I've got a bunch of e to the x's, but I could also let it be the thing under the square root. So I could let it be the whole square root, or I could let it just be the thing under the square root. Do you guys have a preference about which one we do? Okay, so most of you are saying whole. Sorry to those of you that said under. It really doesn't matter. So that means we would let u squared equal to x e to the x minus e to the x, and then 2u du is equal to the derivative of the first times the second plus the first times the derivative of the second minus e to the x. So this right here was our product rule. Which leaves me with 2u du is equal to, check out what happened. It turns out that the derivative of the inside was indeed that thing in the numerator, even if I didn't see it right away. So we're going to have that this is equal to 1 over that whole square root, that's u, times 2u du. And notice the u's cancel out. So this is actually just the integral of 2 du. What's the integral of 2?
Nothing.
That would be the derivative.
Oh, I'm thinking backwards.
Yes. So we actually tack on just a u. And then we'll end up with 2, the square root of x e to the x minus e to the x plus c. Hang on, guys. I got to go get my door. I'm going to write the next problem down real quick for you guys to like start thinking about it. All right, you got it, Mariana. Okay, so the derivative of ln x is 1 over x. I don't have 1 over x, I've got 1 over x cubed. So we're going to bring that x cubed up. And because we're bringing it up, we're recognizing that this is integration by parts. So I'm going to add some bounds to this so that we can see how to like do our notation when we're doing bounds. So I'm going to let this be from 1 to e squared. Okay. So you could add e, but like, hang on, I'm just going to do real quick. If I were to separate it to have like ln x over x times 1 over x squared, I could absolutely do the problem by saying let u equal to ln x. So du is equal to 1 over x dx. I'm like, there's my 1 over x dx, but that means I have to solve for x. So notice when I'm solving for x over here, I have to solve for it from u equals ln x. So I end up with x is equal to e to the u. And then I have u over e to the 2u du. And I didn't really make the problem any easier. I turned it into a different integration by parts, which is still valid, right? So I could do like u e to the negative 2u du and do integration by parts from there. But then I've turned an integration by parts problem into a substitution and integration by parts. Not wrong, just not maybe the most efficient way to do it. Okay, so we're going to pick our u and our dv. Looks like most of you have picked, so good job. We can be thinking about this as like LePet. So our u is our ln x and our dv is x to the negative 3. So then we have 1 over x. And then we have negative 1 over 2, x to the negative 2. And then we do our little arrows. Why do I stop and not keep going there? You got it. For sure gets more complicated if I keep taking derivatives. It's not going to get nice and simple. It's not going to go down to 0. It just gets more and more complicated. So then we're going to have that this is equal to negative 1/2 x to the negative 2 ln x plus 1/2 1 over x x to the negative 2 dx. And our bounds, I would stick my bounds on my integral sign here, and then I'm going to stick them here as well. Whether or not you put them right here is really not that important, as long as you bring them back at the end.
Were the bounds already there in the original problem?
They weren't, but Abby had asked how we notate what notation we use when we put bounds. So
Oh,
that's
okay.
why I like added the bounds on so we could see how the notation is going to work out. Okay, so then this right here is actually just x to the negative 3. So I end up with that same integral of x to the negative 3, which gives me negative 1/4 x to the negative 2. And then I have my bounds, which I'm not going to plug in because they weren't part of the original problem. We would have a plus c instead. But I do want to know, what's ln of e squared? Yes, good job. It's just 2. Remember, ln and e cancel each other out. What is ln of 1? Yes, exactly. Good job, guys. This was C. And this was B. Yes, Micah. Ln of e cubed is equal to 3. If you get ln of 0, that's not going to happen yet because ln of 0 doesn't exist, which means that at this point you won't be given that. But shortly we're going to move into something called improper integrals, where we're evaluating integrals on values that aren't necessarily in the domain. And we'll really talk actually in depth about ln 0 then. Okay, so I want us to think about this problem together because I feel like a lot of you have kind of been memorizing the technique that we use and like is it odd or is it even without really thinking about it. So here, our ideal situation, exactly, Fandy, our ideal situation would be to be able to use the Pythagorean identity, meaning that our ideal situation would be to either let u equal secant x or u equal to tangent x. So if u is equal to secant x, then du is secant x tangent x. And if u is equal to tangent x, then du is secant squared x dx. So the question is, can I make one of these things happen using the Pythagorean identity? In other words, can I get the integral entirely in terms of secant with a secant tangent left over? Or over here, we would be asking ourselves, can I get the integral entirely in terms of tangent with one secant squared left over? And we remind ourselves that the identity that we have here, our Pythagorean identity, is that tangent squared of x plus 1 is equal to secant squared. Which one of these is going to work? The first one's going to work because if I pull out, if I pull out a tangent here, so if I pull my secant x, tangent x off to the side, then I have 4 tangents left over. And if I have 4 tangents left over, can I use that identity to rewrite this entirely in terms of secant? Yeah. So then we'll have this as secant x, tangent x, and then secant squared or tangent squared is secant squared x minus 1. And I'm squaring it because it was to the power of 4 dx. So then I'm thinking of this as tangent squared, squared. And then this is the one that I ended up using. And this one I just got rid of because it wasn't helpful. So these are the types of thoughts that should be going through your head when you have these things. Yes, memorize the power thing, know what odd and even means, but also know that what you're trying to do here. So then this secant x tangent x, that's my du. And I end up then with just the integral of u squared minus 1 squared du. Now what?
You could square everything inside the bracket.
You got it. I'm going to like expand my thing. Exactly. So like I'm going to have u to the 4th minus 2u squared plus 1 du. So I'm just like doing my FOIL here when I expand. And then I will have 1/5 u to the 5th minus 2/3 u cubed plus u plus c, and my u is secant. And then you're done. The final answer for C was without the bounds, -1/2 x to the -2 ln x minus 1/4 x to the -2 plus c. Oops, plus c. Because I didn't plug in the bounds in the end. And partying, yeah, sure, we'll do one. Actually, we can do one right now. If no, we'll do this first because a lot of times they show up in trig sub. So if it doesn't show up, then we'll do one. Okay. So I kind of just told you guys, trig sub's gonna happen here. How can I look at this and know that this is a trig sub problem?
There's the two terms, they're equal to each other. So like there's x squared on the top and x squared at the bottom.
The fact that these are equal is actually like, that's a really good like thing to see. The fact that they're the same means that I'm really not going to be able to go on with the substitution. That's not the only thing that would tell me that. Like if I had an x to the 4th on top and a 16 minus x squared on the bottom, then that would also have to be trig sub. So the reason that the substitution's not going to work is because those powers are like multiples of each other. In other words, if I were to try to do my substitution, then I would only have one x left over. The fact that that power is even there exactly is really the thing that's stopping me from doing this. So the power right here, that power being even is kind of like the thing that stops substitution from, that stops substitution from being able to happen. And that clearly shows me trig sub. If I were to have this or this, do you think I'd be able to do substitution? Yeah. So when both of these things, like the u sub, will actually work. And sometimes you can actually follow through with the u sub. The u sub will work, but it will still turn it into a new problem that requires trig sub. That said, in my opinion, it's still worth it to try. If you're unsure, try to see if the substitution is going to work before just resorting to trig sub. You guys might have noticed when you were doing the practice for the midterm, that integral sheet, the first one, there were a few problems that if you did trig sub, they were actually really, really, really long, complicated problems. But if you managed to make the substitution work, if you tried a u sub first, the problem was actually really fast and just like done with, ended up with a really simple integral. So like, yeah, with the cubed one, actually, let's do this problem first, and then we'll do the cubed one as well. I'll do both of them. Okay, so here, this is going to be trig sub. What is my theta going to be equal to? Arcsine, you got it. So this is my arcsine form. So theta is arcsine of x over 4. Which means that sine theta is equal to x over 4, and x is equal to 4 sine theta. So then dx is 4 cosine theta d theta. Okay, so then I'm replacing everything. I have x squared, so that's 4 sine theta squared. I'm going to go down here and deal with my square root. So that's going to be 16 minus 4 sine theta squared, which gives me 16 cosine squared theta, which gives me 4 cosine theta. So then down here, I'm replacing this with 4 cosine theta, but it turns out that my dx is also equal to 4 cosine theta d theta, and those cancel out. And so I believe Parnian had asked if we could do one where we have to use the double angle identities. And notice that that's about to happen in this trig sub that we have right here. So this is actually going to be equal to 16 sine squared theta d theta. For some reason, I feel like I'm missing a constant somewhere. Let me just go back and check and make sure I'm not. I don't think I am. Okay. Good. So now that we have this even power here, we're not able to do the same thing that we were with the tangent secant one. We're not able to like say, oh, I can pull a factor of sine out and write everything in terms of cosine, or I can pull a factor of cosine out and write everything in terms of sine. So instead, I have to use my half angle identity, or my double, I can't remember, I never. So like, if I were to try sine squared is equal to 1 minus cosine squared, that's still not helpful because I still have cosine squared. And that cosine squared is not a known form. So there's no way, I would just kind of, if I use the Pythagorean identities, I just go back and forth between sine squared and cosine squared. So instead, we use the fact that sine squared is equal to 1/2 times 1 minus cosine of 2 theta. If we had bounds here, it would actually be an easier problem. Tia, yeah, we're gonna actually have to here, and you'll see in just a second. So I can't pull out a factor of cosine right entirely in terms of x, so this means that I need to use my double angle identities. Okay, so Tia says, is there gonna be one where we have to use the half angle identities? And the answer is yes, this problem right here. And we'll see why in just a second. The reason is because we don't have bounds. Parneen, if we did have bounds, we would replace them in the same way we did with the arcsecant earlier, right? We would like plug them into our arcsine, we would replace them, and then we would just plug them into theta. But because this doesn't have bounds, we're actually gonna have to do a trig triangle. So let's keep going here. I'm gonna have this as 8 times theta minus 1/2 sine of 2 theta plus c. And this is where our half angle identity is going to come into play here. This sine of 2 theta, I want to replace this with x's. So the question is, how do I replace sine of 2 theta with x's? If I use my trig triangle, then I'm using the fact that sine of theta is equal to x over 4. And my trig triangle has this angle theta right here. So this is opposite over hypotenuse. And then this becomes 16 minus x squared. What's the angle in my trig triangle? Theta. The angle in my sine of 2 theta is not theta, it's 2 theta. So here I'm going to use the fact that sine of 2 theta is equal to 2 sine theta cosine theta. I'm going to use that fact to rewrite this thing. And then I have 2 trig functions just in terms of the same angle theta. So then cosine theta is adjacent over hypotenuse. And I can rewrite everything. So I get 8 arc sine of x over 4 minus 8 sine theta cosine theta.
Isn't it 4 for the second constant?
No, it's actually going to be 8 because this sine 2 theta is 2 sine theta cosine theta. So like these two 2's right here end up canceling each other out. Like if I were to write it out, it would be like 8 times theta minus 1/2 times 2 sine theta cosine theta. Do you see what I mean?
Yeah.
Okay, so now this 4 goes into the 8, and then we end up with, this is 8 arc sine of x over 4 minus 1/2 x, the square root of 16 minus x squared plus c. Okay, any questions about this?
How about if it was sine 4 theta? Would it be 4 sine theta cos theta?
No. I'll answer that in just a second. I'm a little confused as to why what's not 2x, Mariana.
Like, don't you do 8 times x over 4? And the second to
You do,
last
but then
one?
there's this other 4 right here.
Okay, so you have to combine all of them and then,
Yeah,
okay.
so basically I'm saying I have like an 8 and then I have a 1/4 and then I have a 1/4 and that all goes to 1/2.
Okay,
I just like combined all my constants.
okay, thank you.
Okay, okay. And so then the sine of 4 theta thing, if this were sine of 4 theta, then I know that sine of 2 theta is equal to 2 sine theta cosine theta, right? So it would make sense to think of this as sine of 2 times 2 theta. And then it would be 2 sine 2 theta cosine 2 theta.
Oh, okay.
Okay, and then if I really needed to get this back in terms of theta, then again, I would use the same identity here. So I would have 2 times 2 sine theta cosine theta. And then for cosine of 2 theta, we know that cosine squared of theta is 1/2 times 1 plus cosine 2 theta. So I could just solve for cosine 2 theta from here and get that cosine 2 theta is equal to Q2 cosine squared theta minus 1. And now I have everything in terms of theta. Does that make sense?
Yeah.
So like if you look at, go back to when we first did this in class, I think that we actually, we didn't have a sine of 2 theta, but we did have a cosine squared of 2 theta. And we had to like think of it this way right here to be able to apply this identity. So it's always like you're basically saying, I want it to look exactly the same. What do I have in place in theta? Or what do I have in place of x? In this case, it's 2 theta. Micah, what kind of question? This kind of question or the question that we just did? This question that we just did is super typical final and midterm. Like, I'm going to say that you shouldn't hope that. You should figure out how to do it. It's probably going to be there. So the midterms are, the way that the midterm works is we had this semester, since midterms are kind of like a new thing. This is actually the first semester we're ever doing them in your class just because of the online nature of this semester. So what's happened is there was a template that was made and we had like a list of problems and we basically just have to follow that template. So I'm following the same template as for the science program, but I still like am making your test myself by following their template. The final, you'll have the same final. Almost the same final because there are a few things they do that we don't do. So then those problems are changed accordingly. Okay, so I'm going to do this x cubed one just to show you guys the difference. I know that we've done this in class a few times, and plus it showed up quite a bit on your midterm prep. But just to show you how, if you recognize that substitution works, your life can be better. So here I'm going to let my u equal to 16 minus x squared. So then u squared is equal to 16 minus x squared, because I had took the whole square root, and then 2u du is equal to negative 2x dx. Or in other words, u du is equal to negative x dx. And then I'm just going to multiply by a negative. Okay. So then we need to solve for x squared, and we get that x squared is equal to 16 minus u squared. So I have negative x squared is 16 minus u squared. That negative x dx, that's u du. So I'm going to have u du, and then over my square root, which is just u. And notice here, this is just negative 16 minus, 16 minus u squared. Or in other words, the integral of u squared minus 16. And so then I get 1/3. And this was a much faster problem. Sorry, I know I just did that really fast, but there's not much to see once you've done the substitution. The like challenging thing that happens here is like making sure that you recognize that you can use the substitution, and then remembering your UDU and seeing that you can cancel those things out.
I noticed in the midterm prep that like
Yes.
all of the questions that had like roots, but then you had to either like cube them or put them to the fourth or whatever.
Mhm.
You always put it as a fraction. Does it matter if we leave it as a root and then just cube the root?
You mean is like you write this instead, like the square root of 16 minus x squared cubed?
Yeah.
Yeah, no, it doesn't matter.
Okay.
Yeah. So could I have done this question with trig sub? Absolutely. But just like, honestly, which do you prefer? Do you prefer this or do you prefer this? So like, it is worth it to take that extra 5 seconds to check if your substitution works if you're unsure. Because if it does, then you're going to save yourself like 5 minutes or more. Okay. Are there any questions about the difference between these two problems here?
I have a question, but it's not about the difference between these two. I'm just, would it have changed anything if the x2 was on the, like the denominator?
It would have. We'll look at that really quickly. If I had had this, I'm still going to go forward with the same substitution because I can, but I would be multiplying by negative x on top. I'd have my negative and I'd have an x down here. So then what I'd have here is x to the 4th that I would have to replace. So I would get negative, and then this would be 1 over 16 minus u squared squared. That square root is u, and then my dx is u du. And you can still go through a substitution. Absolutely, Amelia, if they were next to the 5 on the top. So in this case, in this particular case, this turned into 16 minus u squared squared on the bottom. And I can use trig sub here, but I want to point out that I could also do this. I could also say that 16 minus u squared is the same thing as 4 minus u times 4 plus u, because that is a difference of squares. So I could think of this as negative 1 over 4 minus u squared, that's a plus sign there, my bad, times 4 plus u squared. And I could also do a partial fractions on it. So turning this thing, having that x cubed in the bottom, we were able to follow through with the substitution. It turned into a problem where that wasn't much easier though. Harney, I don't understand your question.
So we have 2u du equals negative 2x dx. Why do we take the derivative of both sides again?
I didn't. I just canceled out my 2's. So I just divided both sides. by
Oh, okay. Okay.
That makes sense? Okay. So
Yeah.
in this case, it turned it, okay, so anyway, okay. In this case, it turned it into a problem where I could do trig sub still, or I could do partial fractions. So it didn't necessarily make it easier, but it did give you another option in the case where you're really not comfortable with trig derivatives. But let's say that instead of having 16 minus x squared, I had x squared minus 16. Just really want to like bring this home. If I had x squared minus 16 dx, then what would happen is my u would be still that. And then my u squared is equal to x squared minus 16. But then in this case, my u squared is equal to x squared plus 16. And what would change is just, I'm not going to do this all the way through unless you guys really want me to. But here I would end up with x squared plus 16. Oh my gosh, I'm trying to go through this too fast. Okay. X squared is equal to u squared plus 16. Okay, so if, in other words, instead of having 16 minus x squared under my square root, I had x squared minus 16, this is what I would end up with. Can I do partial fractions on this? No. In fact, if you guys remember, we had the video of like the end forms of partial fractions. This is already a partial fractions end form. Abby just said it. That's irreducible. U squared plus 16 is irreducible. So in this case, unfortunately, they're literally, even though the substitution worked, I have to do trig sub. In other words, there was no possible way for me to avoid trig sub, right? That's just like, I did the substitution. Okay, but guess what? I still have a trig sub. So substitution worked, but I still have to do a trig step. But that said, was it necessarily wrong to take the time to follow through with that substitution? Absolutely not, because it could have ended up saving me an immense amount of time. And if I give you this problem on a midterm or a final, I'm allotting less time for it than I am for this problem. So that is an important thing to keep in mind. Okay, are there any other questions about this type of stuff? All right, then we're moving on to F. So I've had a lot of questions about this and about when to use method 1 and when to use method 2. And the answer is you can always use method 2 and you can always use method 1. And so it's largely a personal preference thing. But that said, starting off with method 1, in my opinion, is always the best way to go. If you have zeros to plug in, plug them in, because then you will go into method 2 already knowing some of your numerators. So at this point, I've plugged in my zeros and I found C and I found D, and I have 2 things left to solve for. So I could plug in 2 other values and use those to solve for A and B, or I could switch to method 2. My suggestion would be that you've only got 2 things left. You might as well move forward with method 1, but it's not wrong to move to method 2. So with that said, because I only did one problem in class with method 2 and I've had so many questions about how it works, I think I'm going to do method 2 here. Is that okay with you guys? Okay, so could stick to method 1 or switch to method 2. So the reason that switching to method 2 is sometimes not worth your time if you don't have a lot left to solve for is because the expansions that take place can actually take a long time to do. And like the writing down the equation can actually be quite long. So here I'm gonna have x minus 6 is equal to a, I'm gonna do this in 2 steps, x cubed minus 2x squared plus b times x squared minus 2x plus c times x minus 2 plus dx cubed. So x minus 6 is equal to x cubed times a plus d plus x squared times negative 2a plus b plus x times negative 2b plus c, and then minus 2c. And so then we're going to look at x cubed. And we're going to have a plus d is equal to 0. Because I have done method 1, do I already know what d equals? I do. If I had skipped method 1 and gone straight to method 2, then I wouldn't know what d is, and I would definitely end up with a system of equations. But because I did method 1, I know that d is negative 1/2. So that means that a is positive 1/2. And then I can move on to x squared. And because I did method 1, I was already able, and I knew d, I was able to solve for a, which means that now I can easily solve for b. Well, and now I have everything. That said, I can double check my work if I want. I can go on and I can still do x, so check work. I can say here, well, I know negative 2b plus c is going to equal to 1. So that's negative 2 times 1 plus 3 is equal to 1, and that's true. So we probably are on the right track. We probably did things right. And I can also do my constant if I want. Negative 2c should equal to negative 6, which would give me c equals 3, which we also already found using method 1. So the two methods together actually was quite nice. It stopped me from ever having to do a system of equations. Okay. Are there any questions about the numerators that we just found here? Good. Okay. So then we have the integral of a over x plus b over x squared plus c over x cubed plus d over x minus 2. And then we have our answer. Okay, any questions? Jello, I'm not sure I understand your question. Will there be numbers or math on the midterm? Yes, there will be both numbers and math on the midterm. Oh, I was trying to like somehow turn it into a serious question. Like, I don't know. Yes, there will be both of those things on the midterm. Okay, because I feel like doing these, very rarely are you ever asked to use a specific method. Okay, we're gonna do the last one here, but I kind of feel like this midterm was actually really easy in terms of integrals. So after this, I just opened the winter 2014 one, and I think that it is a better idea of what to expect. So we're gonna look at that afterwards for the last like 15 minutes. So that said, these questions for sure are ones that could show up, but I think that is probably a little bit easier than what you can expect to see. Okay, so thinking the same things as with that tangent secant one, is there a way that I can, I mean that your midterm is probably going to be a little bit harder than this. This is easier than your midterm. Okay, so the answer is yes. What happens if I pull out a factor of cosine? Can I rewrite everything else in terms of sine? You got it. Yes, I can. So I'll have 0 to pi over 2 cosine squared is equal to 1 minus sine squared. So I was able to pull out that factor of cosine and have everything left over in terms of sine so that I can do this. That's my du. And then if x1 is 0, then u1 is sine of 0, which is just 0. And x2 is pi over 2, then u2 is pi over 2. Oh, sorry, sine of pi over 2. What's sine of pi over 2? 1. You got it. Good. So we will have the integral from 0 to 1 of 1 minus u squared over 1 plus u squared du. What should I do from here? I could separate, but I'm going to separate in a very specific way. Yes, Tia, you got it. Good job. My degree on my top is 1. My degree on my bottom, I'm sorry, 2. My degree on the bottom is also 2. This is special division. So I'm going to rewrite this as the integral from 0 to 1 of negative u squared plus 1 over u squared plus 1. Abby, no, because the degrees are the same. If this were 1 degree less, so if I had like negative u plus 1 over u squared plus 1, then it would be. Okay, that said, I'm going to start by multiplying by negative 1 and negative 1 so that I have negative 0 to 1 u squared minus 1 over u squared plus 1. And then I just need to add 1, minus 1. So negative u squared plus 1 over u squared plus 1. So that gives me 1 minus 1 over u squared plus 1. And I did separate an arctan away. So this is negative u minus arctan u from 0 to 1. What's arctan of 1? You got it. That's my pi over 4. And what's arctan of 0? Tan of 0. Where does tangent equal to 0? You got it, 0. So this is going to be pi over 4 minus 1 minus 0 minus 0. And my final answer is pi over 4 minus 1. Oh, because I forgot, lovely, I didn't write 2. Yeah, that should be a minus 2. Thank you. So that's minus 2 arctan, 2 arctan. That's 2 times pi over 4. And we have a pi over 2 here. Thank you. Thank you, guys. Yes, you could also do long division there. No, Mariana, it's 1 over. So like the known form is the integral of 1 over x squared plus a squared dx is equal to 1 over a arctan of x over a. Uh-oh. And yes, you could also do long division there, but it will just be longer. And you guys might be noticing that the faster you do things, the better. Okay, so I just want to spend the last 5 minutes here looking at these 2 problems from another test, just because I feel like one thing that didn't show up on this test, that we did at all, is completing the square. So that probably means it showed up somewhere else on that final, just not in the integrals. I've never seen a midterm or like a final not have completing the square on it. So like you can expect for sure to have a question where you have to complete the square. So I just want to look at these 2 right here briefly, because I think that they're a good level based on what we've been doing. This first one is just confusing. So what do you guys think we could do for the first one? So I'm seeing a lot of like integration by parts or separating the ln with the ln rule. The integration by parts is definitely a thing that you might see, because you're like, well, that ln right there would be my u, and then that would be my dv, and I do know how to take the integral of that. But the ln derivative would just be like gross. It wouldn't be pleasant. And I could separate my ln with the ln rule, but that doesn't really get me anywhere. Remember that the first thing that you should always think about when you see an integral is substitution, right? always substitution. And like, maybe you don't see a good substitution, but the second thing we're doing, well, actually, first thing is algebra. The second thing is like, force a substitution. So some things that I see that might work here, like things that you could think about would be saying, okay, well, u is equal to 1 over 1 minus x. Now, the reason that I think maybe something like that is because it's similar to what's on the outside. Another u would be the thing, the whole thing inside of my lawn. So maybe I'm thinking of that first u because I know its derivative is outside. Maybe I'm thinking of the second u because it's the whole lawn. So like picking a u with a problem like this that just looks really, really unfamiliar, very different from like the forms that we're used to seeing. Picking a u and seeing what happens is going to be useful. So I'm going to see what happens with these u's. So over here, my du is going to be the derivative of the top times the bottom minus the top times the derivative of the bottom divided by the bottom squared. The fact that the bottom squared showed up is a really, really good thing. So then my du here is 1 minus x plus 1 plus x over 1 minus x squared. And notice what happened here. Did I get exactly what's on the outside? So like when I look at this problem, I did not know that was going to happen. Honestly, like before I started this problem, I wasn't sure that was going to happen. But I did think of all of the techniques that I had and said, I know I should be thinking about substitution first. Because I can't do these derivatives in my head really easily with the quotient rule, I'm going to try it. And guess what? Yay. It worked out. Ln u is a known form. So ln u, remember we thought of it as ln x, but ln x we said you should just memorize as x ln x minus x plus a constant. Okay, and then we replace our u's to get 1 plus x over 1 minus x, ln of 1 plus x over 1 minus x, minus 1 plus x over 1 minus x plus a constant. So like not immediately like jumping to integration by parts or some other method, remembering that we're always supposed to start by fully thinking about all the substitutions possible was the thing that made this problem a reasonable problem. Does that make sense? Good. Okay, so we really don't have time, but I like this question over here because it has this factor on the bottom where you're gonna have to do a completing the square later. So like hands down, when I'm gonna be doing my partial fractions. So I'll have a over x plus 1 plus bx plus c over x squared plus 2x plus 10. That polynomial right there is irreducible. So this right here, this is that special like fixed form where we force a substitution and then complete the square. So even though we don't have time, my recommendation would be to try to do this problem. Make sure that you can get through it. Because it has the thing, like for me, it has the things that could show up that didn't show up on the integrals that we did today. All right. Also, don't forget, area under the curve is on your midterm. I was gonna not have a participation today, but yes, Abby, I think that's a great plan. This will be your participation problem. So I do think so. I think the main thing that's missing is that there were no no partial fractions that involved the arctan. Yeah, I'm gonna be in office hours. Wait, no, office hours are already over today. Office hours today are over, but tomorrow morning 9:30 to 10:30, or if you need me later in the day, you can let me know and I can be available. Yeah. So yes, I'd say this is a pretty good summary. It had like the trig stuff. It had partial fractions with multiple things. It had the trig sub. And then we also went through and did a problem that was substitution that didn't require trig sub. So we covered that. Like it had a integration by parts. So the things that are missing from this review here are largely covered in this problem that right here that starred. We didn't have any like completing the square or any partial fractions that involved an irreducible quadratic. Another thing that's missing is the boomerang technique. So another thing that didn't show up in the integrals we just did is boomerang. But other than that, I'd say it's a pretty good summary if you like add in boomerang. That's my opinion. Like I would say, Pernian, that's usually a good plan is to start by saying, what U subs could I make happen? Especially if it's unfamiliar, especially if you have a problem like what we have over here, the chances of it being a U sub problem are high. So like really take the time to say, can I make this U sub work? And only when it doesn't, move to another method. Any other questions? Yeah, boomerang is going to be your trig times your exponential, exactly. All right, then we're done, guys. Let me know. Like I said, I can be available tomorrow afternoon if you need me. I'm really just going to be like doing like behind the scenes work. So if you need me tomorrow afternoon, I can be around. So please don't hesitate to MIO. Also office hours 9:30 to 10:30 tomorrow.